Hi, my name is Chang Po-Yao. I'm the first author of this poster titled Enabling the Use of C++20 Unseq Execution Policy for OpenCL. I'm a graduate student from Programming Language Lab at National Tsinghua University, Hsinchu, Taiwan, and I'm advised by Professor Jacqueline Lee. Today we're going to go through motivation, C++ parallel algorithm, Unseq in C++ for OpenCL, experiments and result, and summary. C++ has been gaining traction. Exhibit A, C++ for OpenCL, was introduced last year by Anastasia Stulova et al. But the support of standard library was nowhere to be found. We explore the use of execution policy as in C++ parallel algorithm, and we put an eye on state execution Unseq, which was later introduced in C++20. Inspired by OpenCL vector type, we want to make functions with state execution Unseq work as if OpenCL vectors was used. So as of C++20, there are 4 instances of 4 respective execution policy types defined in header execution. They are seq, par, unseq, and unseq. The first 3 of them are defined since C++17, while the last one was introduced later in C++20, and the last one is our focus. For example, this for each call may be vectorized. Note that the first argument is unseq. We observe that OpenCL vector are represented as LVM vector in LVM IR. So a scalar addition would be mapped to just add in LVM. And while an int for addition will look like add NSW4I32 in the LVM IR. Hence, in the LVM IR layer, we vectorize functions with unseq policy and make it run as if we used OpenCL vector. What the OpenCL driver deal with OpenCL vectors when compiling Speedup v2 with target assembly is out of our concern and out of our reach. According to C++20 standard, execution policies are unspecified classes, and state execution Unseq is just a global object of type unsequenced policy. Hence, we can define the execution policy types as follows, as shown on the slide, and define a global object Unseq of type unsequenced policy accordingly. And note that the execution policy types are actually defined as empty classes, empty user-defined types in this case. And we overload functions with execution policy types. And for each call with unseq, resolve to this call, this for each call that receive unsequenced policy, and there is a client directive that hopefully will vectorize this for loop. So if succeed, this for loop will then be vectorized, and the function object f will then be inlined. And if for each call with unseq will not resolve to these 2 functions, which are sequential code. The experiment environment, we use OpenCL 2.1 host site API and CLAN 10.0.1 to translate C++ for OpenCL into LLVM bitcode. And then we use this LLVM SPIR-V that was built against LLVM 10.0.1. We use this SPIR-V translator to translate LLVM IR to an actual SPIR-V binary. And both CPU and GPU runtimes are used in this experiment. This is the C++ for OpenCL compilation flow. So a C++ for OpenCL text file, a .cl file, will be translated by CLAN into LLVM bitcode, and it will be vectorized if needed. And then this bitcode will then be translated into SPIR-V binary by LLVM SPIR-V. So it will finally produce a .spv file. Then on the host side, we leverage OpenCL 2.1 API, which will take a SPIR-V binary as input, and I will invoke OpenCL driver to translate this SPIR-V code into a graphic assembly. This is the Speedup with various vector width. So we benchmark against several kernels. There's 1D convolution, SAD, bilateral filter, permute, and column to image, some of which are run on both CPU and GPU. SAD stands for the sum of absolute differences, which is used by video encoders. And we use unoptimized kernels as the baseline, which are compared against vectorization with 4 and 16. And the last three kernels are from OpenCV 4.5.1, run on GPU. So the baseline is represented as blue bars, and vector width 4 are represented as orange bars. Vector width 16 are represented as gray bars. And this is just what I said. So this work brings the part of C++20 parallel algorithm to C++ for OpenCL, primarily on sequence policy, and some useful functions like for each, transform, inner product, and transform reduce. Results vary from kernel to kernel, probably caused by vendor's graphics compiler, which turns SPIR-V into the actual machine code, and the nature of GPU. In the case of SAD on GPU, vector width 4 results in a speedup of 3.4, and vector width 16 results in 6.9 times speedup, which is the best case. So that's it. Have a good one.